Going to be here to talk about closed loop systems because we really are at a changing time where the likelihood is that for patients with type 1 diabetes is going to be a huge shift in what we're going to see in terms of treatment and burden in the near future. What we get asked in clinic every day is with young people who are diagnosed with type 1 diabetes is, when is this going to be cured? And it's interesting because 100 years ago there was no even treatment for type 1 diabetes, and there was no cure in that respect. And when insulin was first reduced and we could give that to people with type 1 diabetes, this was heralded as the cure for type 1 diabetes. But what it did is meant people would live longer, but then were then exposed to what we now know, the complications of type 1 diabetes. And then over the last century, you saw the slow sort of process of new things coming on with glucose monitors, then insulin pumps in 1978, the first ones. Then 1979, my year of birth, was the first time you could measure HbA1c. And then insulin pens came out and big trials showing that you should get glucose, but it was quite slow and iterative. But then just like in evolution, there was this explosion that's really happened in the last 10 years in terms of technology. So we've got the new generation pumps in 99, you could measure ketones, but then CGM was available in 2000, and the long-acting insulins. But then really from 2004 to 2016, we start seeing this technology shift where smart pumps with calculation whizzes in there, combining pumps and CGM for sensory-augmented pump therapy, and then adding some math in there, or an algorithm which then starts to adjust insulin, or at least put brakes on insulin automatically. And that's where we are now. And then in 2016, the FDA, which is a big regulatory body in America, has just actually in the last month approved the first artificial pancreas or hybrid closed loop system in the United States, and that's going to be released to market early next year. That's going to be a real game changer. I'm going to come to the results for a study that let that FDA approval come later on in the talk. And so during those last 10 years, we saw all those improvements, and with that, we saw this HbA1c shift. You can see early 90s, HbA1c on average in our clinic was up by 10.5, and we would shudder at that now. And then it comes down the right nicely to 8%, and this is through a lot of things, through education, better teams, better glucose monitoring, better insulins. And we've sort of sat here around about 8% for the last few years, and we really want to drive that down. We're hoping that these technologies will herald that change. This is a little bit of a thing that we see. I deal mainly with teenagers, and I just want to give you some perspective about how HbA1cs go through the lifespan. So on the bottom, you've got the age in years, and on the left-hand side, you've got the HbA1cs. And this is data from the Type 1 Exchange, where you're looking at, as you age, what your HbA1c does. And we've got this window here between about 10 to 25, where as adolescence exaggerates everything in life, it sure exaggerates with HbA1c. And this line down here that I've cut is what our target is. These are set by the ADA, American Diabetes Association, what we should be targeting for HbA1c. And less than a third of our patients actually reach that target. And that's our real challenge that we're trying to get to, and hopefully technology will aid us in that. So technology is regulation of the way we live, the way we listen to music, the way we talk with each other, the way we go on holidays. It's definitely going to change the way we manage diabetes. So let's just quickly walk through what we've seen. These are slides. Thank you to Professor Jones at the front about some of the early work that he's done here, where we've got the first pumps in Perth, in Australia was done in Perth. And then by 2016, now half of our patients in our clinic are on insulin pumps. But still, the adult physicians who are out here today are about to be hit by that pump tsunami as our generation works through, because at the moment less than 10% of adults are on pumps, but that's going to shift as our generation of patients shifts into that clinic. So what's a closed loop system? Well, really it's a combination. There's a glucose sensor that delivers data in real time every 5 minutes. You've got a pump which delivers the insulin, and then a math program called an algorithm in the middle, which listens to that data, it listens to what the pump's doing, it listens to the glucose data, and then will modulate insulin in real time. I'm going to go through some early progress, and then I'm going to talk to you about the big trials that have now happened, which are really exciting. So there was some early progress, a lot of funding went into these from the big funding organisations in the world. We've got some algorithm development, which was first in computers, and then in humans. The engineering that we needed to provide for those artificial pancreas systems had to improve. So the glucose sensors, they had to be able to connect it through radio frequency. They had to be sorted out. the pumps had to be more wearable and easy to use and be able to now be overridden by these algorithms. And then there was an explosion of different ways people could do these algorithms. There's not just one single way for an artificial pancreas to work, and really the terminology is changing. So while you've all heard the terms artificial pancreas or closed loop, you're not going to hear those terms in the next 3 or 4 years. The terminology is really changing to this thing called automated insulin delivery. And how that automation is through many different ways, and different companies are all getting the bandwagon with these different types of algorithms. And they'll all work, but they'll all be quite different. So there'll be a real challenge for us as clinicians to be understanding how these different algorithms work and which algorithms for the best patient, because there will be some that will be tailored for other people. This is just looking at the work around the world. I'll skip over that, but Western Australia has played a really key role in that development of the artificial pancreas on the stage. So just to highlight how quickly things have changed, so Directive had this pathway about how they thought the artificial pancreas would work, and it was going to be 6 steps. It was like and I won't talk about it too long, but what's really interesting is that just this year they've scrapped that, said it's gone too fast, we're not going to use those steps anymore. We've now just got a really simplified step. We've got suspend, which we've got now, right? We've got a pump, you put it with a sensor, when you're low it'll stop insulin. We can do that now. Then we've got predictive suspend. We've got that now too. That's the Medtronic 640G pump, where you've got a pump and a sensor. It can see that you're going to go low, so before you get there, it'll shut off the insulin. That's great. So we've got an off tap. We don't have an on tap yet, but that's coming. So now you've got 2 things here: automated insulin delivery. So that's all those closed loop delivery devices as a big umbrella, and then multi-hormone, which really is looking to do both things that a pancreas can do in terms of diabetes, which is insulin and that key hormone glucagon, which can rescue you if you're going low. And they're quite different systems, and they'll work different ways, but they're both being developed in a rapid way. So let's look at that progress. 2006 to 2011, there were lots of proof of principle studies done in teenagers and adults, pregnant mothers, toddlers, new onset type 1 diabetes, most of them done in small clinic trials under carefully controlled scenarios, so that was all done safely. Then it was moved on. This is one of those first studies. I'll skip through that because I think you all want to see what's happening now. There's some early clinic studies. This is more interesting. I don't have a pointer, but what I really want to highlight for you is this time overnight. If there's anything that's more anxiety provoking in type 1 diabetes, it's that fear of hypoglycemia overnight. And what the closed loop systems are really good at doing is modulating that background insulin in terms of keeping you in a nice tight zone overnight. If you're running low, it'll just give you less insulin and it'll make sure you don't carry on low or even get low in the first place. If you're running a little bit high, it'll bring you to that target nicely. I'll come to the studies we did, but what we would say to them is, don't worry, just go to sleep, you'll wake up, your blood sugar will be 6 in the morning, don't worry about it. And it was amazing for them. They really felt that whole anxiety of going to bed at night, of the unknown was going. This is great. Here's Hillary Clinton's Blackberry Storm phone that we used, and you can see here how the progress. I'll show you some slides of modern systems here, but look at this. You've got a Blackberry phone, you've got a pump, you've got 2 sensors, you've got this carrier. We had a laptop you had to monitor them with. Like this was a whole clinic infrastructure to keep these people out of practice. This was ambulant, but because they could walk around these systems, but they had a lot of connectivity, and it was really it was all about feasibility, how it could work, and it did work excellently, even these new ones, but it wasn't really something you could take home. And this is just to set the results from the study, where I'll try and talk you through it. On the left side is blood glucose, so it's in American units, and in the bottom is overnight time from starting closed loop. What you can see is that red dash line is what the algorithm is trying to get the blood glucose to. So the patients would come in, it would get them down in, and it would reduce insulin. This is the insulin delivery on the bottom line. It's like, oh, we've had enough. It would come up and just bring you 150, which is about 6 millimole per litre. And you can see they all woke up spot on. This is looking at the paradigm we use for seeing how good an artificial pancreas system is how much time you're spent in a target range. And this just goes through different ranges, so very low, quite low, perfect, a little bit up, and really high. And look at this, in closed loop they spent 85% of the time in target range. which is really highly successful. And what's really nice is that we get this reduction in hypoglycemia. Traditionally, patients who are using pumps or injections to try and achieve this, more time in target range, end up getting too much hypoglycemia. And that's the beauty of an artificial pancreas system, is that you reduce that time spent hypo while keeping time high, and that, sorry, wrong word, high, keeping a large amount of time in that target range. But it was quite a full-on system, right? Pump, some old sensors, this is bionic man, right? So you got, it's pretty hard to use this around, but then what you've seen is that we've got this really shift to these neat systems where you've got a pump and a sensor, and the algorithms are embedded in these. This is an older pump system, but the new Medtronic pump with the algorithm isn't much different from that. So it's just one sensor and it's all connected up without all the rest of the paraphernalia that was required in the early settings. So not only is the maths and the engineering improving, but the usability of the systems has improved a lot. So what are we going now? So from 2012, people got the confidence of they've done it in the lab, in the little clinics. Let's let them out. First they did it in a hospital system, which was really just moving hospital to a hotel, like it was all the same, but just in a different room. It wasn't on the same site anymore. Diabetes camps, let's move the hospital to a camp, follow the patients around with machines, but we're still out, let them run around, it was good. And then campuses, and then really at home, and it was right, okay, we've done all these things, and we're feeling that confident with the system, go out and use it and see how we go. First of all, it was supervised and then unsupervised. And then we've moved on to randomized controlled trials really to see and test this artificial pancreases at home. And there's lots of systems out there. I've compact them all on one slide. So the 670G, that's the top left-hand system. That's the one that's about to hit the market in America. There's others. There's this one, which is a pod-based system with a phone. There's this one here, the Bionics islet cell. You see it's got two tubes coming out. That's the multi-hormone one. That's the one with glucagon and the one with insulin in it. So it's likely that all these companies are really chasing to try and, it's going to be market-driven and commercialised. So everyone's really running hard to try and keep up with the play, get their systems out. And the challenge for us, I guess, as doctors will be to understand how they work and what systems are best for which patients. They aren't, as we're learning, they're not just plug and play. You're going to have to know how they work and which one's best for which person. So quickly, the Medtronic hybrid closed loop system, it's integrated. It's called hybrid closed loop because you've still got to announce your meals, you've still got to count your carb and push your buttons and bolts, but all your background insulin is sorted out. And it's adaptive, which means that it learns, which is quite fascinating. So it looks at your total insulin requirement from day to day, and as you the aggressiveness of that maths program will depend on that total daily dose. And I've got some data to show you that. This is one of our volunteers, and we're sending them out, about to go. This is Anna Manning from Medtronic, one of the engineers. And the adaptiveness is really nicely shown here. So this is the days at home with the closed loop system. And on the top is the mean blood sugar levels. You can see it improves with time. And the bottom is the percent time spent in range, where initially it took a little getting used to it, but there's got this trend where you get better and better. It's because the algorithm starts to understand the patient and how it works. So it's pretty smart technology. This is the same system in a hotel scenario, really comparing sensor augmented pump therapy with hybrid closed loop. You can see the lines. This is still more feasibility. The lines sort of sit nicely together in terms of how well they perform. But this is what's called the pivotal trial. So this is anyone who's been listening to closed loop talks online or wherever will hear about this pivotal trial, which is where they use this hybrid closed loop system from Medtronic for 3 months and 124 patients in America across many sites. And it wasn't controlled. They didn't have someone else. They didn't have a comparison. They just put everybody on it and tracked them. It wasn't about comparative. It was all about safety. But what they did find is that overall in the study, they spent over 70% time in that target range, which is really good. And this HbA1c shift of 7.4%. So these are really well controlled to push further down to 6.9%, which is pretty really impressive HbA1c in highly motivated patients. Research done in centres with a lot of expertise in closed loops. They knew what they were doing. They knew how to train the patients. this is the publication came out that looked at, everyone worries about side effects from these systems because people don't want something that's out of their control. It's something that we don't like doing. We want to know what we're doing. And look, I just want to show you here that there's a little bit of skin irritation, a little bit of hyperglycemia, a bit of rashes and things. They were really picking at straws to find anything that happened wrong in the study. And what my message here was that there were over 10,000 days and nights in the study, and there was not a single episode of severe hypoglycemia and not any DKA. So it's a really safe system. So that's the Medtronic group. So the FDA trial, the pivotal trial in America. There's Roman Havorka in Cambridge who's running a really strong research unit and really leading the field there with his system. It's a basal rate modulation again. It's a slightly different algorithm. He doesn't have a commercial partner, but that will come. And they're publishing in New England Journal of Medicine, so one of the biggest impact journals there are. And this is a trial that came out for 3 months. This is the longest trial that's been published with a comparison. This time they're comparing closed loop to control, which is central venous pump therapy. And on the left-hand side is the adults, and on the right-hand side is children and adolescents. So, and the results are summarised at the top. So in adults, there were 33 of them, 68% time in range, and the A1C dropped comparatively with between 7.6 and 7.3%. So improved control and more time in range. On the right-hand side, the children and adolescents didn't do so well because they're adolescents. But look at this. If I could point it, I would really love to. It's this bit here that we really like. This bit at night. You can see that in that magenta colour. It doesn't matter what they went to bed with. By morning, they were good. And that's just great. You know, if any of you out there with type 1 diabetes will know, starting the day with a blood sugar of 6 is going to be a good day compared to starting with a blood sugar of 2 or blood sugar of 15, or if you've had a hypo overnight, it really wrecks you. And this is another way that people are presenting the data. This is really cool because it takes in lots of different ways of looking. I'll just talk you through it. So on this side, you've got your sensor glucose from looking between the two groups. But they've got circles as well. And circles is the amount of time they're spending hypoglycemia. So you'd expect someone who's got really good control, it's pretty hard to make them better, but they might improve their hypoglycemia rates. And look at this circle. Well, I've got really good control. My mean blood glucose is really good, but I'm suffering a lot of hypoglycemia because of that. That little circle shrinks down on the closed loop systems are really good. And then you can see the similar thing in children and adolescents. They all come down, not only the mean glucose, but also the amount of time they're spending hypoglycemia. Those little circles are getting nice and small. So it's a nice way of looking at both data visually. Again, in this case, the Cambridge group, there was, in the adult group, there was 1 episode of severe hypoglycemia, but they weren't in closed loop. In the children and adolescents, there was 1 participant who had 2 episodes of severe hypoglycemia, and again, it was not in closed loop at the time that they occurred. So if they were in closed loop, they probably would have been protected. What about our adolescents that are really crappy control? You saw our graph at the start. I wanted to give you that sort of perspective of our adolescents. It's the group that we're really impatient about, I am especially. And this is a very recent publication looking at patients with that poorer control with HbA1c on average of 8.5%. It was only 3 weeks in time, but look at the difference between those on the closed loop and the magenta and not closed loop. Like the whole time, they're almost completely separate, 2 different people really. And again, you can see all their sensor glucose values come down, and all that time spent hypoglycemia, those circles. I mean, a lot of these patients are so hard they don't get any hypoglycemia, but those who were had less. No severe hypoglycemia, no DK. It's only 3 weeks, but these are teenagers who are more challenging. Bionic pancreas, so this is just shifting again to the other group. So I've talked to you from the Medtronic group, the Cambridge group. This is the group in Boston who have got a bionic pancreas, and they were looking at a younger age. So I've looked at adults and adolescents. This is just nice to give you a perspective. Does it work on even younger children? Different systems, but again, just talk your way through it again. This time we've got triangles too. So triangles are for hyperglycemia, circles are for hypoglycemia, and the lines represent just what their blood glucoses were like. So they all came down, and all the circles got smaller, and all the triangles got smaller. So really you're looking at all those nice parameters where you've got sensor glucose improving, less hypoglycemia, less hyperglycemia. And I guess we can talk a little bit about variability and the importance of that for people's quality of life. And this is what these systems are really achieving for people. Again, no severe hypoglycemia and no DK in pre-adolescents. So to summarise or cap that, look at the progress we've made from the early insulin pumps in the 1990s to these first feasibility studies, at-night studies, hotel studies, and then really coming through to these outpatient studies and this pivotal trial and then the FDA approval now, and we'll see the release of this hybrid closed-loop system in America and then hopefully in Australia within a year or two. I'll just skip through that, but what's important is that when you think about closed-loop systems in patients with type 1 diabetes, we often focus just on glycemia, but really it's more than that. It's about the burden on the patient, how much easier life would be, the burden on those caregivers. And so we're embarking on an Australia-wide study. Is Joey still here? Joey's in the back here. He's going to be an adult site here, looking at this Medtronic system and comparing it to standard therapy. And we're going to look at all these markers of psychology, including health economics as well, because it's really important. Not only it's great to have technology, but you've got to convince those people holding the purse that we should be able to purchase this for people who've got type 1 diabetes. We do have some challenges. You still got to count your meal. You can't just go and eat whatever you want, and it's interesting to think about that in terms of how patients might change their behaviours. Do they think that suddenly they can just go and do whatever they want? You know, you can't quite do that. There's still going to be those issues. Technical issues. Sensor accuracy's improved a lot, so that's mainly overcome, which is great. We would love a faster acting insulin. If we had that, then we might not even need to bolus for a meal, and we could use the automatic system to do that, but we're not there yet. That's the way these slides work. There are ways of making insulin quicker, but they're still in development. But I think what the most important thing here is, the last one is translation. Like, we don't know what any person's going to do with technology once they've got it in their hands. There was a recent talk in Valencia that Professor Jones and Professor Davis were at, where one of the nurses who had been running the studies was talking about the experience of the young person. She showed this photo of this teenager about to hold onto a massive ice cream, thinking, don't worry, I'm going to be sorted, the system's going to do it for me. So there's going to be some really significant, interesting ways that people start to behave with this. You know, are we going to cure their type 1 diabetes but not cure their obesity? We've had nice talks about obesity today, so it's going to be interesting, and other challenges that will come into it. And then, of course, we have to train, everybody has to learn how to use these systems. It's a big barrier to make sure that these systems are used effectively. And then, of course, we've got to make sure that people are funded. So let's see in the future how these systems work. There's really positive data out there in terms of their glycemic data. It's going to be really interesting to see how people behave with them. I think that we're opening a new can of worms, perhaps. I think your talk of pre and post diabetes. Yeah. You might revert to some of your pre-diabetes, what that would do for your lifestyle generally might be interesting. So in summary, closely or automated insulin delivery is a term that you should get used to. It represents a new paradigm for diabetes management. This will transform care positively, but also interestingly. And we must understand how it works for patients and as clinicians to make sure that we initiate this in a positive way, in a way that's really beneficial for everybody. So of course, thank you for the team. Professor Jones, Professor Davis were both here, trailblazers in the area, and really it's been a pleasure to be part of that team and introduce the team to carry on, and then everybody else. It's a big team we have to make it all possible. And then, of course, the patients who have given up their bodies and their time to be part of this, to make it real. Thank you very much.